All right, let's talk about rocket engines. Specifically, we're going to dive into a really elegant solution to a massive engineering challenge. It's a surprisingly simple idea, but it's one that has totally shaped the history of spaceflight.
So think about this for a second. A big rocket engine needs to just gulp down insane amounts of fuel and oxidizer. We're talking tons every single second. And it has to pump all that propellant into a combustion chamber that is, well, already a raging inferno. So how on earth do you do that?
I know, it sounds kind of weird, right? To get your main engine roaring to life, you've got to fire up a little mini engine inside of it first. But this beautifully simple and, yeah, maybe slightly counterintuitive idea is the absolute key to one of the most successful designs in the history of rocketry.
To really get why this is so critical, we have to frame the problem the right way. We are literally feeding a beast. The pumps you need to force propellants into that main combustion chamber, they need a colossal amount of power. I'm talking more power, in some cases, than an entire nuclear submarine.
And the solution to this huge power problem is a design called the gas generator cycle. Now, it does have its trade-offs, and we'll definitely get to those, but its reliability and relative simplicity have made it the absolute workhorse of spaceflight for more than half a century.
Okay, so let's properly introduce the star of the show, the gas generator cycle, or as you'll hear it called, the GG cycle. This is the engineering choice behind some of the most legendary rockets that have ever flown.
So at its heart, the concept is actually pretty straightforward. You basically bleed off a tiny percentage of your fuel and oxidizer, you burn that in a separate, smaller combustion chamber, that's your gas generator, and you use the hot gas that comes out of it to spin a turbine. And that turbine is what powers the massive pumps for the main engine.
Okay, so take a look at this diagram. It pretty much lays out the entire process. See up at the top? You've got the fuel and oxidizer pumps. A little bit of that propellant gets diverted into the gas generator, the GG. The hot gas from that powers the turbine, which then drives the pumps. And then, the exhaust from that turbine, it just gets vented overboard, while the main flow of propellant goes right into the main combustion chamber, the CC.
All right, now let's actually trace the path of the propellant step by step. It's like this beautifully choreographed mechanical dance. It's really cool when you see how it all comes together.
Okay, let's follow the flow. First, those turbopumps, and they're just incredibly powerful pumps driven by that turbine, they start pulling fuel and oxidizer from the tanks. Right away, a small amount of this gets sent over to the gas generator and ignited. This creates this super powerful stream of hot gas that just shoots through the turbine, spinning it at tens of thousands of RPM. And since the turbine is on the same shaft as the pumps, that spinning action is what powers them, forcing that main flow of propellants into the combustion chamber at just immense pressure. And here's the key part. That hot gas from the turbine, it just gets dumped overboard, a lot of times through its own little exhaust pipe. And that last step, dumping the turbine exhaust, that brings us right to the heart of this design. The gas generator cycle is what you'd call an elegant compromise. It's this brilliant trade-off between engineering simplicity on one hand and raw efficiency on the other.
This is what's known as an open cycle design. What that means is the propellant you use to power the pumps is, well, essentially lost. It does its job, spins the turbine, but then it's just shot out the side without really contributing any significant thrust. It's kind of like using a little bit of your gasoline just to run your car's fuel pump and then venting the pump's exhaust straight into the air instead of into the engine.
And this slide right here, it just lays out that core trade-off perfectly. The gas generator cycle puts simplicity and reliability first over raw efficiency. It's way less complex to design and build than the more efficient closed-cycle engines, which route that turbine exhaust back into the main engine so you don't waste it. But that extra plumbing in closed cycles, man, that adds a ton of engineering headaches.
So you might be asking yourself, has this trade-off been worth it? Well, the answer is a resounding yes, and you can see it in the incredible legacy of this slightly wasteful design. It has powered some of the most iconic rockets in all of history.
I mean, just look at this list. It's a hall of fame of rocketry. The F-1 engines that lifted the mighty Saturn V to the moon. The Merlin engines that power SpaceX's Falcon 9 fleet today. The RD-107 on the Soyuz, which is the longest-serving rocket family in history. For every single one of these, engineers chose reliability over getting every last drop of performance. When you're sending people to the moon or building a commercial workhorse, proven often beats perfect.
And the F1 engine? Wow! It's the perfect example of just how capable this cycle is. Even as a gas generator engine, it is still the most powerful single-chamber liquid-fueled engine that has ever flown. It just proves that this simple design can achieve absolutely monumental power.
So, what's the big takeaway here? The gas generator cycle is really the ultimate pragmatist's engine. It accepts a small hit in efficiency, but in exchange it gets a huge gain in reliability and simplicity. And that engineering choice has been proven right time and time and time again, from the launch pads of the Cold War all the way to the reusable rockets of today.
And that leaves us with a really fascinating question for the future, right? As engineers develop these new, more efficient engine cycles, will the elegant compromise of the gas generator cycle continue to be the winning choice? Only time is going to tell if this proven workhorse will remain a cornerstone of space exploration.